started. Again, tight schedule, so let's. So this is Jasper. Not going to even say the last name again. He's the CTO North America for Riscure, and really nice enough to step in. Had presentations in his back pocket. Asked him to cut it down to about 30 minutes, so we have 30 minutes and 5 minutes for Q&A, and then we'll go into the next one. Like I said, that'll probably eat up a little bit of break, and I have to talk to Brian about starting his talk a little bit later, but I think it's going to be well worth it, so please help me give a warm welcome to Jasper. Thank you.
Thank you. Yeah, so my name is actually pronounced Jasper van. I'm originally Dutch, so that's the official pronunciation. Yeah, I had to cut down my talk a little bit. So originally it was 20 ways past secure boot, but well, just by the mighty hand of God, I made 10 ways just magically disappear. So we'll talk about 10 ways past secure boot. So just an overview of my talk. I'll first give an introduction on what secure boot is. Maybe rise of hands. Who knows what it is? Secure boot? Who knows what it is but didn't raise his hand? Okay, we got a few. So I'll split it up into two main categories. One is the more logical threats, which is the threats you're probably more familiar with. And then I'll talk about hardware-related threats. So I work for a company called Riscure. I'm the CTO for our North American office. And we deal, in a nutshell, with embedded security. So what kind of threats do you get additionally when all of a sudden an attacker can hold your device in their hands? And a lot of people think that security completely breaks down at that point, but I would argue with that. Anyway, I've been testing on all kinds of devices. I'm not going to list them out all. So I'm originally from Amsterdam. I have a background in, well, pen testing, but also computer science and artificial intelligence. Well, let's get started. So I'll first talk, I'm going back to my title slide. There. So I'm going to be talking about secure boot, specifically in embedded devices, because that's the space that we operate in. I'm not specifically talking about the UEFI or Microsoft Lockdown or things like that, but it doesn't entirely mean that it doesn't apply. So it's the same types of mechanisms that are being used there. And there's actually an interesting parallel there that you're seeing in the PC world. I don't know if any of you are old enough like me, I feel old nowadays, to remember DOS and boot sector viruses. Yay. So one of the ideas behind the boot sector virus is you actually load yourself before the antivirus loads. So that way you can defeat any of the mechanisms in there. And that's actually what I like to call kind of a race to the start. So you'll see that a lot in embedded devices, but also on the PC, that if you're malware, you want to boot before the antivirus. And if you're antivirus, you want to boot before the malware. So there's this race going to the start. So in the PC world, you're seeing a lot of things happening with locking down BIOS, so it can't be changed anymore, signature verifications in UEFI. But I said I wasn't going to talk about that, so let's go to embedded devices. It's actually pretty much in most consumer electronics nowadays. You'll see secure boot. So you'll see it in your game console, you'll see it in your mobile phone, you'll even see it in your, that's a ECU on the bottom right there. Set-top box for digital TV. All these devices have some kind of security function that they're trying to protect. And one of the mechanisms to do that and to prevent these kind of races to the start is to make sure that at least you're booting authenticated code. So that way you can control what code is on your platform, and you can prevent harm against your security. So who really wants this kind of secure boot? Well, it is kind of a double-edged sword, especially you guys are a bit from the hacker community as well. You want to run all your own code on your device. So you want to be able to actually break secure boot and load everything you want. There's a downside to that as well, though. If you lose your phone and you don't have something like secure boot and all the other security mechanisms, I don't know about you guys, but my Gmail account and all that stuff is linked to my phone, which is, is linked up to all my password recovery mechanisms. So it is also there to protect you. At the same time, it's also there to protect the business case for the appliance and the device vendors. So they want to make sure that their IP is not stolen. They want to make sure that only authenticated code is running on their devices. They want to implement things like anti-rollback, so they can only, when the security patch comes out, only newer firmwares can be run. So I don't want to get into a whole political discussion, but this security boot can be used in different ways. So the idea behind it is that we start off when a processor comes up, you start off in an environment that's really hard to change. So it's, as soon as the CPU comes up, it will actually start booting ROM code first. This is the first thing it does. ROM, as the name implies, it's read-only memory, so it's really hard to modify unless you get into the chip itself and physically start modifying the ROM. So you can be pretty well assured that that's, at least against non-government type hackers, that's pretty secure. So what that internal boot ROM does, its only purpose in life is to load the external firmware from Flash or eMMC or whatnot and verify a digital signature over that. So we'll actually make sure that the Flash image is authentic before it even runs that code. Now, for various reasons, there's usually multiple stages of these bootloaders, and at some point the last bootloader is in charge of loading the OS, and the OS is in charge of loading the application. So it's this whole chain of trust that you can build this way, where one component just checks the next and checks the next and checks the next. So this is one example of secure boot on common Android platforms. So if you have a phone or a tablet in your pocket that runs Android, you'll see something. You could see something like this. So first of all, the internal boot ROM loads, which loads a first stage bootloader, which is typically proprietary for whatever platform you have. Now somewhere down the line, if they're using U-boot, I don't know if you guys know U-boot, it's an open source bootloader for embedded devices. And you can use that to load your Android kernel. Another interesting thing here is that not only is each bootloader in charge of loading the next one, it's actually also in charge of locking down the system. So a lot of security features in the hardware and in software are configured during boot. So the first piece of code that loads has all privileges on the entire platform. So you can access all memory, you can access all hardware, but somewhere down the line you're going to have to lock that down. So you'll see that happening during boot. Who knows what trust zone is? I'm getting blinded. So a trust zone is actually probably in your pocket. So a lot of Android phones, at least ARM platforms, have this feature. And it is a hardware feature that virtualizes one of the CPUs into a secure world and a non-secure world. And I can talk a lot about that as well, but that's not what this talk is about. But keep in mind that in the secure world, there's actually a completely separate OS running there. So there's an OS that you're not going to see that's running besides Android. And in the secure world, you just have a lot more privileges than in the non-secure world. That's what you're going to keep in mind for this talk. So the idea is you'll start off in the secure world, and then once you're ready initializing and locking down, you load U-boot or Android, which will then run in the normal world. Now, I've been talking about secure boot as in making sure that you run authenticated code, which of course doesn't mean that the authentic code is perfect. So just having secure boot is not a sufficient condition for having a secure platform, but it's definitely a necessary condition for having a secure platform. So if somebody has an exploit in userland, they could still pop that and elevate privileges. It gets harder when you have to circumvent hardware security privileges. So it might be easy to get from user space into kernel space by having an exploit in your kernel driver, but going from for instance, from normal world in trust zone to secure world, that's a bit harder if you need to do that through a hardware exploit. Anyway, if these things fail, you have possibly arbitrary code execution. Sometimes you can have persistence attacks. So, for instance, if during your boot chain a flash upgrade is locked out, then normally down the chain you can't write the flash anymore. But if you could do that earlier on before it's locked down, you could have some malware persistence issues there. And this can be a stepping stone for further attacks. So if you're able to inject code, you may be able to dump out some previously inaccessible memory areas. So let's go through the logical threats. So one of the things, and these are kind of based on things that we see in general when we're doing these kind of evaluations of secure boot. I've had the luxury of being able to scratch out the 10 least interesting ones in my opinion, so we get the 10 best ones here. So one of the things is when you're doing a firmware upgrade, you got to make sure you're actually also doing this kind of signature verification over the firmware image. So not just on boot, but also when you're doing the upgrade. I've seen issues in the way that the firmware was structured, which parts were actually signed, order differences, all kinds of weird stuff. So it's something to really look at when you're doing flashing of code. One of the main things here is you want to make sure that you don't put too much functionality in your firmware upgrade. Just make it dump that image into your flash after doing a signature verification, and that's it. One thing to take into account is also rollback. So rollback is the idea is you have an authenticated firmware, you find a bug in it, so as a vendor you want to upgrade and roll to the new version, but your attacker would like to use the old version with the bug in it. So there are ways where you can make sure that you only roll forward to newer versions and never back to old versions, even though the signature is still valid. Another thing that you want to take into account is if you have debugging functionality that you do not need in the field, it's actually useful to have all that stuff disabled in your production build and have a separate internal manufacturer-only build that is signed and that has the debug features built in. Because then even if somebody breaks a security mechanism, they can't access those debug features in the field. Still need to keep your debug firmware internal, of course. Other things we've seen is boot code is getting pretty bloated nowadays. So more and more functionality is added. And well, we are all aware of security here, so more functionality just means more probability you're going to have a coding mistake somewhere. And there's a drive for this because you want to boot from all kinds of different media. You want to have restore mechanisms, fallback mechanisms, firmware upgrade mechanisms all built into your boot code. But you get the traditional logical problems like buffer overflows, sign problems, overflows, etc. And I put a couple of links up here where you can find these things. So the mitigations are also the traditional ones. So we've had a couple of interesting talks about fuzzing and symbolic execution, but also code review, just a human inspection helps. And of course, trying to really limit your functionality to what you need is also a way to mitigate this. This is one of my favorite ones. So I like crypto. So one of the things that people don't always realize that if you encrypt the firmware, that doesn't mean that it's integrity protected. It just means that an attacker cannot easily see what the code is. But if you just flip a bit in an encrypted firmware, there may be a predictable effect in the decrypted version. For instance, a really cool example is if you're using AES in CBC mode. So it's just a way, as you maybe know, AES takes in 16 bytes, encrypts it, and outputs 16 bytes. But our firmware is bigger than 16 bytes, so we need to somehow apply AES to the whole thing. So you have these different chaining modes, and CBC is one of them. And CBC actually has the property that if I, in the encrypted version, that I, supposedly I can't read what the actual code there is. If I flip a bit there, I'm going to have, in the decrypted version, I'm going to have one block that's entirely garbled. So 16 bytes will be garbled. But in the next block, I'm going to have exactly that same bit flip at the same index. So it's a very predictable effect in my decrypted version. And all the other blocks are not affected. So you can imagine if I now do that to, let's say through some other exploit, I did manage to get a dump of this firmware. So I can only read it, and I can only write the encrypted version. But now if I find some interesting security check, and security checks always end with some conditional branch, if pin accepted, then do this, or if signature accepted, do this, otherwise do that. So that's a conditional instruction. So now I can start flipping bits in that conditional instruction very predictably by just changing the ciphertext. And I will garble 16 bytes before that, but if that's in some different function, for instance, who cares? So really, crypto is hard, as you know. You really want to make sure that you also do a integrity check beyond your encryption. So first verify the integrity of the firmware, the encrypted version, and then decrypt it. You can also use different modes besides ECB and CBC, like GCM, which is an authenticated cipher. So it has authentication and decryption built into one. Trusting headers. This is actually an interesting one because your firmware image is going to have some structure with headers and sizes of blocks and all those kind of things. And usually those blocks are signed individually. Fine. A problem with that is that in order to parse those headers to find out where the signature is, you need to parse the headers, which is at that point still unverified data. You haven't verified the signature over it yet. So there's a bit of a chicken and egg problem going on there. So you want to really make sure that you, before doing the signature check, you are really sure that all the lengths and all the pointers and stuff are within the bounds that you expect them to be. So there's no malicious input there. Because you cannot check the signature on it yet, so you've got to do some extra verification that there's no malicious data in there. So let's move on to the hardware-related threats. They're getting more and more interesting, aren't they? So one of the things that people in software don't always realize is that there's also such a thing as hardware debugging. JTAG is actually a standard for doing hardware debugging, and it can allow full and low-level control of your execution, just like you would have in like a kernel debugger or something, but actually at one step lower at the hardware level. So I can suspend the process, I can single step, I can actually scan and figure out what all the states of the pins are on the chip as well. So there's a lot of control that you get with these types of hardware debugging mechanisms. And they're pretty much on every device. So different things that manufacturers do are, the worst thing is if you just leave the complete header on the PCB, so an attacker can just plug into it and they're done. The next step that I've seen is they remove the header, so we have to resolder the header. It's also not very hard. It gets a little bit harder when they remove the PCB traces. So JTAGs are actually physical pins that are coming out of the chip. So one of the tricks, and this doesn't work always anymore, but you can actually start, when you know the pins, if they're on the outside, you can start resoldering wires. That still works. If it's a BGA chip and all the balls are at the bottom of the chip, we've had some success with guiding wires between the balls and trying to reconnect, but it gets hard at that point. Anyway, the most important thing is to just disable JTAG on the CPU side. So again, that's some flag somewhere internally in the CPU that they can set. Some chips allow you to password protect JTAG, so you cannot use it until you've supplied a certain magic string. But that, of course, has some inherent dangers if you leak that string. The solutions are a bit chip dependent, so it really depends on how the hardware is implemented. But do lock it down if you can. Also and related to JTAG, you often see debugging consoles on UARTs. So basic serial ports where all the boot flow is just printed out. U-boot has a really nice interface as well to serial. And they actually found a nice bug here in the NUC a couple years ago, where U-boot was doing a signature verification, but on the serial ports, they actually allowed you to interact with the console of the U-boot. And the U-boot has a very nice feature. You can, I don't know if you guys can read it, but this is MD, which means memory dump. And there's MW, memory write. So somebody actually dumped out the firmware, figured out where the signature verification code was, and then if you just overwrite that one instruction again that makes the decision whether the signature is correct or not with a no-op, boom, you're in. So it's nice that they implement signature verification, but don't give the attacker console to fully control all memory, because then things break down again. This is an interesting thing on ECUs. So often you'll have different boot modes. So in normal operation, it will just boot. So ECUs, if you guys are not familiar, those are the things that control your engines in cars. So they're little embedded systems with a very well-specified functions. But they often have to go into maintenance for a firmware upgrade or for readout of the engine, historical data. So they actually have different boot modes depending on what kind of connector you plug in there, what kind of switches you set, or what kind of strap you close on the PCB. And sometimes this actually disables all signature verification. So once you know how to pretend to be such a cable, or if you know which strap to override, you can just circumvent any kind of secure booting on those platforms. So it's an engineering problem, I understand that, but for security you don't want to have any way to run unauthenticated code. So you need to check that. Then there's this nice talk to you, time of check, time of use vulnerabilities. So that's a common term in security where you check some kind of state first, and then later you're going to use that state. But that later implies there's some attack window for an attacker to do something to your system. So you can imagine, and this was especially common in smaller embedded devices and more resource-constrained devices, if you don't have a lot of memory to copy your firmware into some secure RAM, you may actually just do a signature verification over your firmware and then have the CPU directly execute instructions from this firmware. Now, it doesn't seem like a problem because you've checked the firmware so you can execute it, right? The problem is that usually these flash firmwares are a separate chip on a PCB with a nice bus going to the main CPU. And this bus is actually something that an attacker has, at least if they have the device in hands, they can probe, manipulate, do whatever with the bus lines. One of the cool attacks that we did, it's already a couple of years ago, we had an embedded device that had such a signature verification over the flash. But actually the flash was only used for about a third or something. So they actually put in a bigger flash than that was needed. But this gave us an interesting loophole, because what we did is so the top of the flash, the top third or so, was the actual device code with the signature. So that was what was checked. And then all the rest wasn't checked, because you don't need to do that if it's just empty space. But we put our own code basically with a huge knob sled all the way to the end, and our evil code at the end. And now if you look at memory addressing, there's usually a memory bus and a data bus going to the flash. So what we did is we intercepted one of the address lines, actually one of the high bits in the address line, so we could physically move the value of that, or set it to a 0 or 1. So what actually happens, it was executing the top, checking the top, and then as soon as it's done finishing its signature verification, we push that address line bit to the high value. So the CPU thinks it's still reading and executing from that top part, but the flash controller, because that one bit is now set to high, is actually reading from the high part, which is what we have under control. So obviously not good. It was actually interesting because the timing was not very specific, so we actually did it with a button that somebody could press. So we had games going on who could press it at the right time to get our code to execute, and it was not as hard as we hoped it would be. So the check there is the way to fix it is you load your code into some protected area and then execute from there. And that depends on your platform whether you have such an area or not. It says DRAM here. DRAM doesn't have to be internal to the SoC either, so it could be external as well. But it is a much faster bus, so it's actually harder to do hardware attacks on there as well. But it's not a foolproof fix. Timing attacks. So I'm actually going to go straight into the example, because I hear the next talk is actually being done by Darth Vader, and that's not a guy I want to upset by going over my time. The idea, and this is actually an example from the Xbox 360. This is a published attack. They compare the HMAC, which is a signature over the actual firmware, to one that they've computed internally. And they check it byte by byte. And here's actually a side channel attack where you can see, just based on the time it takes to check the HMAC, whether it's a correct, the time to check the HMAC corresponds to the number of bytes of the HMAC that are equal. So consider it a password check. So it will check the first byte, see if it's correct. If it's not correct, it terminates. If it is correct, it goes to the second one, and then terminates. So just by measuring the time, you can figure out which byte is correct or incorrect. So this is not our work, but some guys made a board to automate this on the Xbox. And the idea is that I'm putting a rogue bootloader on the Xbox, so this HMAC check will fail, but I'm going to measure how long it takes to actually report that failure. Now, I'm going to start with first having a HMAC value of all zeros. Now, I just increase the first byte to 1, and then 2, and then 3, and then 4, and I keep on measuring the time. If at some point all of a sudden the time increases, then I know that first byte must have been correct. I could just rinse and repeat this attack to find each byte individually by, well, it takes a few hours actually. Normally you have to brute force through the entire HMAC, which is way too much. But if you can do it byte by byte, it's actually doable in a couple hours. And this allows you to run arbitrary code on the Xbox. So my last one is glitch sensitivity. On Monday I did a whole course on this kind of stuff. The idea is that as soon as you have hardware access to a device, you can also start affecting the way it executes instructions. You can actually introduce faults in the way it executes instructions. So one way is to do glitching. So you actually control the power supply to a device, but you drop it really quickly, exactly at the time that the instruction that you're interested in is executing. And that may actually introduce a fault. And one of the faults we see is that you can make that instruction almost disappear. It's like it was changed into a no-op. Well, if this is happening right at the moment when your boot code is checking a signature, and it's deciding whether the signature is correct or not, you may just bypass that skip entirely. So there's a lot of fault injection literature out there. I just want to show you oh shit, I have 6 seconds. Am I going to make it? No. So I'm going to just do the last slide. So really, don't think of this as secure or insecure. It really depends on what the function of your device is, how many security features you want to implement. If you are getting access to your bank account and you maybe have a couple $1,000s in there, which sucks if somebody would get it, but no nation state is going to spend millions trying to get into your bank account. If it is the nuclear launch codes, it gets a little bit different. So really think about what the attacks are that are relevant to your device if you want to implement countermeasures. And if you have high security requirements, then all these kind of hardware mechanisms as well apply as well. But just designing things properly and not screwing up already makes a big difference. So learn your lessons from the past and pay attention to detail. Okay, I just want to wrap up. I don't know how many time I have for questions. Silent. I have time? Okay. I see Darth is already waiting in the back there. So